Okay, so up next, we have a deep dive into WebGPU from Wei Jie at Geometry.
Thanks, Chloe. Okay. So, hi everybody, my name is Wei Jie from Geometry, doing research and development. And my topic today is WebGPU for crypto. So, but before we begin our presentation, let's generate a ZK proof in our browser because we want to do some transaction. And it's taking a really long time. That's a problem. Client-side ZK tends to be pretty slow, even for circuits which are reasonable in size for privacy-related applications. So how can we make this faster? Just to drive in the point about performance, in applications like tornado cache, depends on your machine, but it takes 10 to 30 seconds. On my really old machine, it takes like 20 seconds. And for other circuits, like the Persona Labs efficient ECDSA verification circuit with 163,000 constraints on an N1 MacBook Pro, 39 seconds. So that's not very good user experience. But it's still necessary to generate ZK proofs in the client for these applications, because otherwise you would have to outsource your proving to a third party, and the third party can easily de-anonymize you, and that defeats the purpose of doing privacy in the first place. So where do we go from here? I want to introduce the idea of using WebGPU for crypto client-side proving. So WebGPU is a relatively new API for the web. It's a standard by the W3C. Big companies in the browser space like Google, Microsoft, Mozilla, Apple were all involved in the creation of this API over the past few years. They started working on this in 2017, and I believe that soon it will be available in these browsers, Chrome, Firefox, Safari. But currently, it's still very new, so you have to enable this feature in your developer features in your config page. And WebGPU comes with its own shader language. Shader language is basically the same. It means a programming language that you send to your GPU. Or you write programs that you send to your GPU in a shader language. Okay, so all this is relatively new because it's targeting modern GPUs, and it provides layers of abstraction which are more developer-friendly than previous iterations of GPU for the web, like WebGL. And it's also much friendlier to write these programs or shaders than lower-level languages like C++ with CUDA or with APIs like Vulkan. So much of the WebGPU development today is focused on graphics. There are lots of examples online. You get 3D, high performance, high FPS graphics with WebGPU, but this presentation is not about that, because WebGPU also supports general purpose compute, not just graphics. And the whole point of using GPUs in the ZK or crypto space is because you want to parallelize your operations. And the benefits of doing that in this domain is that certain algorithms can benefit from running different computations in parallel. So Inoyama does a lot of work on GPUs. zkParis has certain competition tracks to award prizes to teams that can write code for GPUs. And there is also a lot of interesting speed-ups in domains like private information retrieval, where you need to do a lot of matrix multiplication. So that's where GPUs come in. And so all that stuff has to do with server-side GPU and server-side acceleration with GPUs. But what about client-side? So because web GPU is so underexplored, I have observed that this domain is very underexplored. I think there's a lot of space for engineers and developers and researchers to jump in. And so even if you don't have like a big GPU cluster, why not use your own device, right? You can develop these interesting applications that speed up different algorithms on your own device. And they run on most devices, most modern devices. This is a really old phone, 2019 era phone, and it runs WebGPU in the developer version of Chrome. So in terms of like what we want to target for research and development into WebGPU for crypto, like examples of algos will be multi-scalar multiplication and NTT, number theoretic transforms. And there has been some research on whether these algos are amenable to GPUs or FPGAs. And there is a lot of like complexity in this analysis. You also have to look into how memory access plays a role in the actual performance that you get out of this. But nevertheless, it's very exciting to have a new field to jump in and do this research. So I just want to spend a bit of time to go into a technical overview of WebGPU. So the most important thing to remember is that it's an API, and the browser does all the heavy lifting. And if you can wrap your head around the basic programming model of WebGPU, it's relatively easy to get started programming with it, because it's really not as complex as something like CUDA with C++, for example. There are abstractions over, for example, an adapter. A GPU adapter is an abstraction over like a particular implementation of WebGPU in the browser, and it provides you with an abstraction over the device called GPU device. GPU devices can have buffers, storage buffers, staging buffers. These are abstractions over ways that developers can read and write data into the GPU. And this is where it's also important to understand the underlying memory models of GPUs, because they behave differently than with like regular computer architecture. Specifically, it's important to understand how memory maps to different GPU cores, and memory access is very closely tied to computation. There is the idea of a pipeline, and this is abstraction over the way that the API bundles together data in buffers and shaders, which is the GPU code they want to execute, and sends it to the GPU. So there's a lot of new terms in this framework, and it's really, really important to understand the whole paradigm and how this works. But there's a lot of really good documentation by the W3C. There are more and more developers writing code of this and writing articles and blog posts. So I think it's a really good time to start. Here's an example of WebGPU shader language code. So this takes some value, multiplies it by itself, and adds 3 and repeats this operation 104,000 times. And if you benchmark this on a CPU, in serial, it's like half a second. But if you run this in parallel in the GPU, it's much faster, because GPUs tend to have like hundreds of cores, while CPUs have much lower number. So, and this was done on a really old GPU. And this, if you run this on a like M2 MacBook Pro, will be much faster anyway. So I also wrote an implementation of the Poseidon hash function in WGSL for WebGPU. So this is targeting the BN254 curve, a scalar field. If you run more than 2,000 of these hash functions in parallel, then the GPU is going to beat the CPU, or at least on my machine. I did a benchmark on 16,000 hash 16,000 hashes in Poseidon, and for the CPU, it's like 1 second on the machine in the browser, and like 300 milliseconds in GPU via WebGPU. So I did this after I finished my slides, so I don't have like screenshots, but come find me and I will show you the demo. So where can we go with this? So we are still really early. If you spend some time on GitHub and look for WebGPU for crypto, you will only find a few repos. So we are indebted to this MSM WebGPU repo that Sampriti wrote. Sampriti, Nelin, and Aryan, and I'm really grateful for the help. They wrote a lot of, MSM code for, I think, a hackathon or some kind of event at Zuzalu or something like that. So I used the basic field arithmetic, big integer arithmetic functions that they wrote and converted that to use for my Poseidon hash function implementation. So there are also other developers who wrote stuff with WebGPU, but not that many. So if you're an engineer and you want to do something really interesting in crypto, get in the car. Let's go shopping. Okay. And let's take a step back and think about what do we do in a field where it's so new that there's a lot of things to learn and research, but there are not enough developer tools and not enough community groups to support this work. So let's think about how ZK looked like in 2019. And this was when we had the equivalent I'm thinking of is Circom. So in 2018, 2019, Circom was really new. And it was groundbreaking because it allowed developers to easily write circuits. Today, people are using Halo 2 and so on, but back then, Circom was the go-to language for if you wanted to write any kind of circuit. I mean, back then, it was Graph 16, and what the 0x part group did was really awesome because they just jumped straight into it, and then they wrote really useful developer tools. They pushed it to the extreme to write extremely large circuits, and this sort of tested the boundaries, pushed the boundaries what they could do. They got a bunch of developers excited about ZK, and some of them spun out into their own startups. And many of the participants you see at today's event. So what's the equivalent for WebGPU for crypto? Currently, most developers who write WebGPU probably do so for graphics. And there are not that many who write it for crypto. So what can we do? What kind of tools can we write? So maybe debugging tools. There are no debugging tools I've found so far. There are no higher level DSLs that I've seen besides ones that target graphics. There needs to be more research into how we can abstract, build more abstractions that make it even easier to target consumer devices. And we also need to do research into security because I think no one has done this. Is it possible to DOS clients if you provide malicious inputs? I don't know. Can you do timing attacks, side channel attacks to extract private key information? I'm not sure. But this is really important because if you want to do ZK proving on the client side, you need to figure out all this stuff. So moonshot goals for engineers. ZK provers. We want to implement ZK provers you don't have to write the whole thing in WebGPU. You can write parts in WASM or JavaScript and then write the stuff that you need to parallelize in WebGPU. That's perfectly fine. Witness generation, that's also one of the slow steps in running privacy-based client-side apps. And then there are more moonshot ideas like distributed proof generation networks. So you don't just want to you don't just want people with GPU farms to run your apps or your nodes. Maybe if you can run it in a browser, even better. And also applications to PRR. So very short presentation, but thanks for your attention. I'd love to take any questions you have. Thank you. Yeah.
Thanks for the great talk again. Maybe it's a really stupid question, but I've used Three.js, and I didn't have to enable special browser extensions. So,
which OS and browser are you on?
Chrome, M1, Apple.
Mac. Okay, I'm on Linux, and my laptop is really shitty. So
okay.
I don't know. It's different experiences. Yeah.
Okay.
Oh, cool. Thank you.
Amazing. Thank you, Wei Jie.